Okay. Just before starting today's topic, let me tell you one thing. Yesterday, at some juncture in my class, if you recall, while I was showing you the trajectory, so over there, I was considering somewhere, like say once I had shown you the trajectory corresponding to the problem discussed in class. After that, I think again I came back, and then the trajectory, I mean, it looks something like this. It looks something like this. Do you remember this? Do you remember this situation? I had something like this. I had some trajectories. It looks something like this. I think maybe it was at around 1 hour juncture or 49 minutes. Exactly, I don't remember. But somewhere it was something like that, if you recall. Just let me tell you, this was related to. If you look back at my recording, I was using whatever default panel was there. Please remember that this is not related to that problem that we considered, which has complex roots, and they were purely imaginary. Okay, where I had the trajectories as some ellipse. Okay, right? So for pure imaginary roots of the characteristic equation, you are always going to have trajectories like this. Please remember that this was related to some nonlinear functions here. If you go back to the recording, you will see that. Okay, please don't confuse this one with the other one, because this structure and this structure will look something alike. So that is why you may think that this was from the pure imaginary root plus minus 2y. Okay, fine. So now let me move to what I ended yesterday. So if you recall, yesterday I ended with like critical points, and then I embarked on the question of stability. Okay, so basically I am going to discuss whether the critical points that we find, critical points or stationary points that we find, whether those points that we consider, whether they are in stable equilibrium or unstable equilibrium. Okay, fine. And again, I had already told you yesterday about a trajectory, or for that matter, a solution. Of course, the trajectory you are going to get through solution of the, and a solution, I mean, coming back to a critical point or remaining near the point or never coming back to the critical point. These three situations yesterday I told you that we are going to see answers to that. Okay. Now again, in some book you may find the word isolated. They are going to describe the critical points as isolated points. Okay. So, or isolated critical point. So, what is the meaning of that? See, if suppose I have a critical point, say x1. I have a critical point x1. So then, if I can find a, of course, I am considering plane autonomous system here. So, if I can find a very small circle centered at the point x1 in such a way that in this circle, you cannot find any other critical points. So then we say that this particular critical point is an isolated point. Okay, that's it. So the next thing I'm going to do, because see, probably you are thinking that I'm going to start with the solution of some system of equations like this, and then I've described, the critical points or the stability of the solution depending upon the eigenvalue, eigenvector whatsoever. I'll come back to that, don't worry. But before that, I'd like to discuss one particular case, right? In order to clear the concept of stability more. Okay, so I am into the notion of stability, and I would like to explain it through a single differential equation, not necessarily through a system of differential equations. Okay, right? And you will see that I'm going to take a very simple equation. Okay, fine. See, I'm going to talk about the population growth. I'm going to talk about population growth. Say, suppose the variable y, this is a dependent, this is a dependent variable, and t is the time. It is the independent variable. So suppose y represents the population in a particular region of some species at time t. Okay. So now, if I am considering exponential growth, so then what I can do, I can simply model the increase in population with some differential equation like this. Is it okay with everybody? Fine? Right?
Yes.
And where here R is simply the growth rate. R is simply the growth rate. Okay, fine. So you know that if my initial population was something like y0 equal to y0, then you know that the solution is simply given by e to the power RT. Okay, fine. So that means if you want to plot the solution, it is going to look something like, suppose this is t, this is yt. So here, something to t0, I am going to have my initial condition. So here, the solution, this solution, it indicates that whenever you start with, there is always going to be some increase in the population, right? If I, of course, if I consider R to be strictly greater than 0, right? Okay. But this is not a very good model. This is not a very good model. So that is why let me come to the model, which is called logistic growth. Okay. Okay. So what is that? What is the logistic growth? What it does? It takes into account of the fact that the growth rate R is not fixed. This is again going to depend upon, this R is again going to depend upon the population Y. So that is why it should be some function of Y. Okay, fine. And the function should be such that this R, which is approximately equal to this function hy. So this one, what is going to happen? R is it is positive, and what happened? Just a minute. Yeah, it is large. It is large when y is small. When y is small, right? And then this starts decreasing. Basically, hy starts decreasing. Hy starts decreasing as y grows, and it becomes negative for sufficiently large r. For sufficiently, not large r, large y. Okay. So if you consider all these three facts, all these three attributes that we ideally want, so then this hy, if you take it as r minus ay, right? So this is a very good case for substitute hy. Okay. So now instead of ry, now if I write down my equation, as dy dt, so this is r minus ay into y. So this can further be written as r into 1 minus Yeah, I can write it like this, right? Is it okay with everybody? And this I can simply write as 1 minus y by k into y. Okay, where k is a constant. It is simply given by your this r by a. R by a. Of course, I am assuming both r and a to be positive. Okay, fine. So first of all, okay, fine. So now I don't want to solve this equation. I don't want to solve this equation. So firstly, what I would like to do, I would like to draw the graph, and of course now see if you recall earlier when we considered initial value problem, so they were something like this. See, dy dt. So this is f of ty, right? F of ty, right? Under some initial condition, y at t naught equal to y naught. Is it okay with everybody? Is it okay with everybody? Right?
Yes, sir.
Right? Initial value problem that we have considered. So now, if this initial value problem, it has to represent an autonomous system, then what must happen? That variable, the independent variable t cannot exist explicitly on the right side of the differential equation, right? So that is why this is going to be, in this case, because I am simply considering one equation, one single equation, so this has to be a function of y, right? And because here t is nothing but time, so ideally I start with something like this. At t equal to 0, basically now the population is y naught. Is it okay with everybody? So obviously this is an autonomous system. Okay. So now, what I'd like to do, I would like to draw the graph of y versus fy. So here fy is nothing but this function, r into 1 minus y by k into y. Is it okay? Fine. Is it okay?
Yes, sir.
Right? Okay, fine. So now another thing. Now let me just simply now look at this. Okay. So if I want to find out the constant solutions or equilibrium solutions, what I will have to do? I'll have to simply plug in the right hand side to be equal to 0, right? Okay. So then what are you going to get? The constant solution, can you tell me what they are going to be? Yes? From this equation, what are the constant solution?
Sir, y equals to 0 and y equals to k.
Y equal to 0 and y equal to k. Is it clear to everybody? I have simply plugged in the right hand side to be equal to 0, and from there I have found out the values of y. That's it. As easy as that. Is it okay? Fine. So y equal to 0 and y equal to k are my constant or equilibrium solutions. So they are nothing but the critical points, right, for this particular equation. So now let me try to graph this function f of y. Now, if you look at the expression for f of y, this is nothing but f of y. So you see that this is a parabola. This is a parabola, right? So obviously the parabola is going to be something like this. And of course, you know that the zeros of fy, it occurs at y equal to 0 and y equal to k. So obviously this is going to be k. Fine, this is going to be k. Now, if you look at f of y, so this is r into 1 minus y by k into y. So even suppose I can say suppose r equal to 1, because I can always multiply whatever I get with r later on. Say simply consider this one. Y squared by k. So then obviously the maximum is going to occur at what? When this is equal to 0. right? Is it okay?
Yes, sir.
Right? See, I'm trying to draw the parabola. I mean, without going into the minute detail. So through some tricks, with the help of calculus, I'm trying to draw the parabola. That is what it is. Okay. So basically, when y equal to k by 2, right? So that means this point should correspond to y equal to k by 2. Fine. So far, so good. Is it okay? Fine.
Yes, sir.
Now, at k by 2, what is the value of f of y at k by 2? What is the value of f of y? So at k by 2, this is going to be what? K by 2. If you plug in, this is going to be half. So this is r by 2 into k by 2. This is rk by 4. Is it okay? The value of f of y at the point k by 2. Right?
Yes, sir.
Okay, so that means this point is nothing but rk by 4. So the coordinates of this point is k by 2, rk by 4. That's it. So far, so good, right? Okay, so now what other interpretation we can get from here? Now look at this equation again. Look at this equation again. So now I want to draw the graph of t versus yt. But right now I'm not going to do it. I'm going to wait for a little bit again. You know why it is. Okay. So now if I want to draw the graph of t versus y by t. So now see, you know that from y lying in this interval, you can see that f of y is greater than 0. Isn't it? Right? F of y is greater than 0. So if you want to draw the curve of y as a function of t, that curve is going to be monotonically increasing for this. Is it okay? Monotonically increasing for y lying between 0 and k, right? And of course, here you can see that because dy dt that is less than 0, right? Dy dt is nothing but f of y that is less than 0 here. So for k greater than 0, my this y decreasing, and for this y increasing. Y increasing. Is it okay? For the time being, it is fine, right? Are we doing well? Is everybody getting it?
Yes, sir.
Okay?
Yes.
So now, there is another interesting, I'm still not drawing it. I'm holding it back for a while. Now, let us try to find out d2y, dt2, because I would like to find out the point of inflections. Okay, point of inflection for the curve of y as a function of t. Okay, so now this is simply ddt of dy dt, right? And this is say ddt of this is f of y, isn't it? Dy dt is f of y, right? Okay, so this is dy of f of y and then dy dt. Yes?
Yes, sir.
Right? So that means it is f prime y and dy dt is simply f of y. Fine? Yes? This,
Yes, sir.
right? Don't be afraid. Don't be afraid. I mean, sometimes, I mean, when I ask you a question, you may be wrong. What is to be ashamed about that? Nothing. We can correct it again. Fine. So I have found out that this happens. Okay. So I have found out that. Okay. Let me write it down. Okay, this information is good enough. I'll try to make use of. Now, I hope you will appreciate why I have been telling you to go through the chapter on how derivatives affect the shape of a graph. Okay, fine. So this information tells you, we know that, I mean, when this is greater than 0, so that means it is the graph of y is going to be concave upwards. Right? Okay? Fine?
Yes, sir.
Right? Okay.
Yes.
And when it is less than 0, concave downwards. Okay? Right? When does this happen? When f prime y, fy has same sign. Right? Is it okay?
Yes, sir.
Yes, sir.
Right? Okay. And this is going to happen when they are going to have different sign. They are going to have different sign. Okay? Fine? So now, see, your f of y. Okay. This is here the vertical axis is f of y. Okay. And f prime y, this is nothing but the slope of this graph. Isn't it? Because this is y versus f of y. Is it okay?
Yes.
Yes, sir.
Right? So this portion you can see that f prime y, that is positive, right? As well as your y is also positive, right? Okay? Are you getting my point?
Yes, sir.
Right? So in this portion, your y is concave upward, right? And here you can see that f prime y is negative, right? And y is still positive, right? So for this portion, your y is concave downwards. Okay, fine, isn't it?
Yes, sir.
Right?
Yes, sir.
And what is this k by 2? K by 2 is a point of what?
Point of inflection.
Point of inflection, right? K by 2 is a point of inflection. Oh my God, I have so many information here. And what about this portion? What about this portion? This portion, why? Is it going to be concave upwards or downwards? Like when y is greater than k, what is going to happen?
Downward.
Concave upwards.
Concave.
Upwards.
Why?
Because both will be negative.
Yes. Because see here I am not looking for y positive or negative. I am looking for when f prime y
And
fy, right? Here this is fy is negative, right? Because vertical axis is fy is negative, this function is monotonically decreasing, so both of them are negative. So beyond this beyond this, I mean here in this range, your again y is concave upwards. Fine. Okay. Now let me try to draw the graph of yt. Okay. Now here, what are the crucial points you have to remember is that, okay, say this is 0. So firstly, y equal to 0 and y equal to k, they are my equilibrium points or equilibrium solutions. Is it okay? Fine. They are constant solutions, right?
Yes, sir.
Yes,
Isn't
sir.
it? So throughout the evolution, as t tends to infinity, whatever may be the value of t, if you start with a particle, it is going to remain there only. Okay. So okay, this is my y equal to 0. Fine. And suppose this is my y equal to k. Okay. And I still have one more crucial line here. This is k. This k by 2 is also crucial. It is something like this. It is something like this. Okay, fine. So now, what is happening? Let us see what happens. Let us see what happens. Say, for y lying between 0 and k by 2, y lying between 0 and k by 2, what is happening? Y lying between 0 and k by 2, what is happening? Wherever you start with, the curve is going to be concave upwards. Is it okay? So it is going to have some shape like this. It is going to have some shape like this. Isn't it? Wherever it starts with. Are you getting my point?
Yes, sir.
Yes,
Right?
sir.
Then what is going to happen? Once it crosses this, it is going to have concave downwards. So here it is going to be something like this. It is going to be something like this. Okay, fine. And again, like say, in this from 0 from k by 2 to, and what will happen here? So if it start here, it is going to be like this. 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 Okay. Now, when y is greater than k, what is going to happen from here? Again, it is going to be concave upwards. So that means this shape is going to be something like this, isn't it? Are you getting my point?
Yes, sir.
Yes, sir.
Right? Okay, fine. So this is giving you some idea about how the solution is going to be. How the solution is going to be. Okay, you can see that wherever you start with, because say the population, widening the population, it is always possible. I'm not going to go below this 0 line, right? I'm going to always going to above this. So now, wherever you start with, you will see that even when you are starting with some initial condition, which is very near to y equal to 0, it is still going towards the line y equal to k. Is it okay? It looks like, right? If I use all the information from my function f of y, is it okay? Fine.
Yes, sir.
Now, you may be thinking, like say, I'm never allowing this curve to cross the line y equal to k. Can you tell me why? Can you tell me why?
So y equals to k is a constant solution.
Okay, then
So it cannot cross the solution, sir.
why? See, through the uniqueness and existence theorem.
Yes.
And of course, I am assuming all the conditions for uniqueness and existence to be true. Preconditions for uniqueness and existence to be true. So under that prescribed initial condition here, so you remember all these are initial conditions where the graph starts, right? So they can never cross the graph y equal to k, right? So my solution has to be something like this. Solution has to be something like this. My solution has to be something like this with all the information that I have gathered. So that means you know that whatever solution you are going to take, it is going to approach y equal to k as t tends to infinity. Okay, so this y equal to this value k, it is called, probably some of you have already studied it. It is called the carrying capacity. It is called the carrying capacity. Okay. Carrying capacity. Okay. So what is going to happen in the long run? The population is never going to go beyond a certain number. Is it okay? Right? It is approaching k. But never going to be equal to k. We are not allowed that because of the uniqueness of the solution. Is it okay? Fine. So now I'm just simply going to write down the solution. You can easily because see, if you recall, just a minute. If you recall, my whatever may be the shape of the right hand side, my differential equation was this, right? My differential equation was this. So it is, of course, it is something like 1. I mean, 1 by fy dy equal to dt. It is of variable separable type, isn't it? It is of variable separable type. So you can easily solve it. Is it okay? Right? Whatever may be the shape of this, it is always solvable. Easily. You can easily solve it. Is it okay? Fine. So let me just simply write down the solution. Let me simply write down the solution. Why not k? Why not e minus? Why not e to the power minus r? E to the power minus r. E to the power minus r. So from here you can see that if y not equal to 0, the solution is going to be simply y equal to 0 throughout. Is it okay? Fine. Right? And if y equal to k, sorry, y not equal to k, if y not equal to k, so then what is going to happen? This is going to be equal to 0, this part, and eventually you are going to get y equal to k, right? So if you start with y not equal to 0 and k, you are going to get a constant solution, right? And then from here also you can see that as t tends to infinity, this term is going to go to 0. So eventually y is going to be equal to k. Is it okay with everybody?
Yes, sir.
Right? So now what is happening? Now? I think I can. I'll show you in my slides also the summary of this. Okay. So you can see that all of them are moving towards, all of them are approaching y equal to k, right? All the other solutions, they are approaching y equal to k, right? So that is why the solution y equal to k is called, and this is important, asymptotically stable solution. Okay, right? So now you can see that the solution y equal to 0. Of course, here I'm considering the constant solutions only, which is going to be, corresponding to the critical points in a system of equations later on. Okay, fine. So then you can see that here y equal to this 0 line. Even if the initial condition, even if you start with, they are very nearby this, this y equal to 0 line, even then they are deviating from this and they are going some, at least it is not coming back to y equal to 0. Is that clear? Is that clear?
Yes, sir.
Fine. So that is why your y equal to 0, it is called an unstable equilibrium solution. Okay. So now I think the stable and unstable solutions, right? The perception about that, I think, is clear to you now. Is it okay? Fine. See, this is the beginning. This is just the beginning. I'm just showing you an example. Okay. So now I think we have enough material, not really material. We have enough courage to move forward, right? Because we know what is going to happen, right? So stable is simply approaching, unstable is simply going away. That's it. Is it okay? Fine. So now let me just simply summarize. in the slides what we have done so far. Okay. So what here? So this we have already tackled yesterday. All this stuff. This is the notion of stability. So this is the exponential growth I am talking about, right? And this is the exponential growth. Okay. And now let me tell you one thing here. The exponential growth, that the equation we consider, it was a linear equation, isn't it? Are you getting the point? Right? Because the equation was what? Simply dy dt equal to ry, isn't it? The right hand side was linear, fine. Whereas the logistic growth equation that we consider, it was a non-linear equation, right? So this has shown you the difference between the solution of linear and non-linear differential equations. Is it okay? Fine. So now here you can see that these are nothing but the direction field. Okay, so from the direction field also you can have an idea of what the final solutions are going to be. And here you can see that. This is a constant solution. So similarly, this is also a constant solution. Okay. So although I am getting some vectors here, right? But I am not even bothered about these solutions because I am always going to consider your y to be greater than 0. In this particular case, if I assume y to be the population of some spaces, okay, and say this is the solution curve t versus y. Now here you can see that what is happening here. Say this is where the point of inflection is. So beyond this line, the curves are going to be concave downwards, right? And here concave upwards. Here also they are concave upwards, right? And then this is the relation between them. And again, this is the solution. So that is what it is. Fine. Okay. So now I think we have got enough on that. So I'll be doing this agent reduce and shape of functions. But before that, I would like to tell you something else. Okay, I'd like to tell you something else. Okay, I hope now this is clear. Okay, so see, I'm still in the plain autonomous system. But what I'm going to do now, I'm going to do stability of linear systems. Stability of linear systems. So, of course, I mean, system of two equations we are going to do. Please remember. Okay, we are going to do system of two equations. Okay. Now, you may be asking me, like say, when I started with autonomous system, right? The right hand side, it was a function of x and y, right? And I don't know, I have no idea whether the right hand side is going to be a linear or non-linear function. But in most of the real life cases, they are non-linear functions. Okay, the logistic growth function that we had just tackled, you can see that it was a non-linear one, right? So now, can you tell me, despite having all those ingredients, we are still trying to deal with linear system? Why? Yes? Yeah, can somebody tell me? I think I have already answered that sometime back. Yeah, can you tell me?
Sir, if we have the information of this linear system, then this will give some prediction of the non-linear system.
Yes.
Because
so
linear is more simpler.
Yeah, the last line, can you repeat it?
Linear is more simpler.
Yeah,
to study the
obviously.
system.
Linear is more simpler. And you please remember one thing: we can always find somehow. I shouldn't use the word always, but most of the times it is possible to find one related linear system corresponding to a non-linear one. Okay, so that is why we are interested in this stability of linear systems. Okay, fine. And here I would like to tell you one more thing. Okay, fine. So that is why we are going to study, for the time being, only linear system. Okay, fine. So that means you know that I am going to deal with system of equations given by this, where the entries of the matrix A are constants. Okay, entries of the matrix A are constants. So generally real constants. Is it okay? Fine. So now, as you know, that we are interested in equilibrium solutions. Right? And the equilibrium solutions, I mean, they are nothing but constant solution. So basically, you are going to get, say, x to be equal to some constant vector, like say something like x naught, y naught. Is it okay with everybody? Right? Okay. So I will get something like some vector like x naught, y naught as my critical point. Is it okay with everybody? Some point, I mean, some point in the phase plane, right? Where it is, the point is such that, I mean, the solution doesn't evolve there, it remains there. Is it okay? Fine?
Yes, sir.
Yes, sir.
Okay. But despite that, what we are going to do throughout all the study that is going to come in near future. So now whatever study we are going to do, we are going to assume that that 0, 0, 0, 0 is a critical point. 0, 0 is a critical point. You may be thinking why it is so, because any point, I mean x0, y0, you can always through some kind of translation, some kind of shifting, you can always, using some transformations, right? Using some transformation, you can always convert this into this. Is it okay with everybody? Right? By change of
Yes,
variables,
sir.
right?
Yes,
We
sir.
can always achieve that. So, I mean, studying the 0, 0 point in one coordinate system is equivalent to studying the point x0, y0. Fine? So that is why throughout all the further studies, we are going to assume that 0, 0 or the origin is a critical point in the xy plane. Fine? Okay. So that brings me to the fact that, like, now, if I consider this equation, so then if I want 0, 0 to be my critical points, then what must happen? So in order to find out critical point, what we do? We just simply plug in the right hand side to be equal to 0. Right?
Yes, sir.
Yes? Yes? So that means I have to plug in this equal to 0. Right? And I want to get 0 solution as the only solution, because I am seeking 0, 0 as my critical point. Is it okay? Right? For that, what property the coefficient matrix A must have?
Determinant non-zero.
Determinant non-zero. Yes, determinant non-zero. So what we are going to do, like say if I assume say A equal to like say A, B, C, D. I'm following Jiten here. So that is why I'm writing it like this. Right? If this is so, then I am going to assume that the determinant given by this delta AB minus BC, this is not equal to 0. Right? This assumption we are going to make. Okay. So now, with that, let me show you another trick. So we are going to make use of that later on. Now, if I consider the characteristic equation for this matrix, so then this is what. This is equal to 0. So this means your A minus lambda, D minus lambda minus BC, this is equal to 0, right? Isn't it? If my A is this. Okay? So this means your is it okay? Fine. This I can write as lambda squared. See here, what A and D, they are nothing but the diagonal elements, isn't it? A and D are nothing but the diagonal elements of that matrix A, right? Their sum is called what?
Trace.
Trace. So if I denote the trace by tau, so this is going to be tau lambda plus, and this is nothing but this determinant, right? Plus delta equal to 0. Is it okay? Fine. So if I want to find out the value of this lambda, so this is going to be tau plus minus tau square minus 4 delta by 2. Tau square minus 4 delta by 2. Is it okay with everybody? Right? Okay. So that means the nature of the eigenvalues, it is going to depend upon this expression. It is going to depend upon this expression. So, right, say if this is greater than 0, you are going to have real and distinct. right? If it's equal to 0, then real and equal, and if it is less than 0, they are going to be complex. Is it okay with everybody?
Yes, sir.
Yes. So now the remaining study we are going to do based on this. Okay. And for that, I'm just simply going to rush through a couple of slides. Huh? And after that, I will do something in detail. Okay. So you will understand what I mean by this. So what I'm going to do, I'm going to take one particular example. I'm going to take one particular example. And in that example, what I'm going to do, this value of, like say, the discriminant, right? The discriminant, once I'm going to take greater than 0, less than 0, equal to 0, right? And then I'm going to show you the corresponding trajectories there. Corresponding trajectories. Okay. And in my next slide, I'm going to tell you what those trajectories, like say here I am assuming that the origin is the critical point, right? So what the origin is going to be called, the nomenclature of the origin, depending upon the nature of the eigenvalues. Okay, so I'm going to tell what they are called, and after that I'm going to categorize them, and I'll try to prove some theorem related with the nature of the solution. So basically, we are trying to find out the shape of the trajectories depending upon the value of lambda. That's it. Okay, fine. So let me just okay. So I'm going to take. Okay, fine. See, this you can easily work out, and I just don't want to. Consume time there. So here the problem is about finding out the eigenvalues of the linear system, this given by this, okay, in terms of C, okay, and use a numerical solver. I could have done that. I already have MATLAB and P-Plan 9. I could have done that, but in order to save time, I'm just going to show you the final figures. Okay, say here, you know that the coefficient matrix is given by this, okay, and you know that the trace is nothing but the sum of this diagonal entries. This is -2, and the determinant is simply 1 minus c. That's determinant is 1 minus c. So the eigenvalues are given by this. Okay. So obviously, the nature of the eigenvalues are going to be determined by the sign of c. Is it okay with everybody? Right. So firstly, let us take c equal to 1 by 4. So then what happens? Your the eigenvalue is going to be -1 plus minus half, right? So it is going to be -half and -3 by 2. So basically, what you see here, both the eigenvalues, of course, eigenvalues are distinct, right? And they have the same sign. Okay. So now, these are the trajectories. These are the trajectories corresponding to c equal to 1 by 4. So you can see the shape of the trajectories like that. You can see that all of them, they are converging towards the critical point 0, 0. Is it okay? Fine? Isn't it?
Yes, sir.
Right? And here, in all these three figures, they are designating one straight line by different colors than all the other trajectories. I'll tell you about the significance of this line later on. Okay, so this is here. See, in that case, the critical point, the origin, that is nothing but 0, 0. Let me tell you in advance. This is going to be called a node. Okay, so now if c equal to 4. If c equal to 4, so that means this is -1 plus -2, right? So once you are going to get lambda equal to 1, and next lambda equal to -3. So you can see that they are real and distinct, but they are of opposite sign. That is the main thing here. Okay. So then what is going to happen? You are going to get the trajectories to be something like this. Okay, and here you can see that some of the trajectories, they are what? They are asymptotically moving towards this line, right? This line, this straight line. Okay, see, like the one we saw in that logistic growth, isn't it? Right? And whereas they are moving away from the origin. Okay, all of them are moving away from the origin except for the red one, right? Which is moving towards the origin. All of them are converging towards the origin. So this is called a saddle. This is called a saddle. And then if I take c equal to 0, I have the single real eigenvalue that is repeated, lambda equal to -1. So in that case, you can see that they are all, converging. They are all converging towards this, and this is called, again, this is a node. Okay, and then when you have complex eigenvalue here corresponding to say c equal to -9, so then you get all the trajectories. You can see that it is converging towards the origin in the shape of a spiral, right? So they are called spiral. These are spirals. So I am going to describe all of them. And here, so see node is something like that. Where basically this is called a converging node or a stable node. What happens? Everything is converging towards the critical point 0. Okay, so this is a node. So you can have straight lines, you can have curved lines, but they are going to all converge or diverge towards that critical point. So this is a node. So this is a saddle. So here you can see that this one and this one, they are converging. Here all the others are diverging, right? So in this case, this 0 is called a saddle point. Okay, and then this is the example of the spiral. So this I have taken from Simon's book. This is not very clear. You better follow Jill and Kulan's book. It is beautifully explained there. Anyway, I am going to explain it later on also. Okay, so I think this is it till this one. I have just given you an idea how the solutions are going to look like, and corresponding to those kind of trajectories, how you designate. Like say the critical points are called what. Okay, so now let me really start with. Firstly, I will start with case 1. That is nothing but real distinct eigenvalues. Okay, fine. So that is what I'm going to do now. So I think I'll be able to do only one case today, but that is good enough. Don't worry about it. Okay. Okay. Right. So let us firstly assume that my solutions of the characteristic equation, they are real and distinct. And let us assume that my eigenvalues are lambda 1 and lambda 2, and the corresponding eigenvectors are k1 and k2. Right? So then the general solution is going to be x bar. This is equal to c1 k1 e to the power lambda 1t plus c2 k2 e to the power lambda 2. Fine. Okay. And now look at this. This I can write as e to the power lambda 1 t, e to the power lambda 1 t, then c1 k1 plus c2 k2 e to the power lambda 2 minus lambda 1 t. Is it okay with everybody? Fine. I have just made some simple adjustments here. Is it okay? Fine. So now let us take case 1. Case 1. Of course, I'm still into real and distinct. I'm still into real and distinct. Okay. So now let us assume that. I mean they are real and distinct. Okay. Real and distinct. So that means your this one tau squared minus this is going to be greater than 0. This is going to be greater than 0. And then again, let us assume that they are of same sign. So for the time being, let us assume that that subcase as that both your lambda 1 and lambda 2 are negative. Both lambda 1 and lambda 2 are negative. And let us assume that it follows something like this. So lambda 2 less than lambda 1, okay, less than 0. Okay, so obviously here data has to be greater than 0, and this tau will be less than 0 or greater than 0. Tau will be less than 0 or greater than 0.
Less than 0.
Less than 0. So then everything is going. So I am going to get tau plus something, all positive. This is equal to 0. So that is going to give me, the lambda plus something like lambda equal to negative. Okay. So this is the situation I am considering. So that means when both of them are going to be positive, so in that case, tau is going to be greater than 0. Is it okay? Is it okay to everybody? Fine?
Yes, sir. Yes.
Yes? Okay. Fine. So with this information, we can definitely proceed further. And you will see that this is very, very interesting. I don't know whether you find it interesting or not, but I am really, really fascinated about this. Okay. So now, from this information, you can see what we are going to do, whether they are positive or negative. We are always going to do like this. We are always going to assume here that lambda 2 is less than lambda 1, whether they are positive or negative. Is it okay with everybody? Fine. Even
Yes, sir.
in the case when they have opposite sign, what I am going to do, I am going to take your lambda 2, I am going to take it like this. Are you getting the point? Because it has something to do with what I have done here. It has something to do with what I have done here. You get to know. You get to know it soon. Why I'm doing it always. Okay. So now, see, since lambda 2 is strictly less than lambda 1, so obviously lambda 2 minus lambda 1, this is less than 0. Is it okay? Fine. So then if you look at this expression, because see, we are seeking solutions when t becomes large, when t tends to infinity. Is it okay? Fine. T tends to infinity. So
Yes,
then
sir.
what is going to happen, irrespective of whether lambda 1, lambda 2 are positive, negative, or they have opposite sign, what is going to happen as t tends to infinity, this expression, like say the general solution, it is always going to tend to, I mean, C1 K1 e to the power lambda 1 t, isn't it? Are you getting my point? Under the assumptions? Is it okay? Because this is negative. This term is going to tend to 0 as t tends to infinity. Is it fine?
Yes.
Yes, sir.
Yes. So for all these three cases, this is always going to be valid. Remember that. Fine. So now let me come to this first case. Let me come to the first case. Okay. Fine. So and again, let me tell you for the third case, simply your this delta is going to be less than 0. When they are going to be having opposite sign, delta is going to be less than 0. I don't know what is going to happen to tau because it doesn't matter. Is it okay? Fine? Okay, so now let me proceed. And then here you can see that, since as t tends to infinity, your x tends to that c1 k1 into power lambda 1 t. So the eigenvector k1 is going to dominate. Remember that. The eigenvector k1 is going to dominate. I will explain that to you, how it dominates in terms of the trajectories. Okay, I need some color here. Okay, fine. So now I am taking the case when lambda 1, lambda 2 are both negative. So you know, irrespective of I mean, whatever happens to this, what is going to, like as t tends to infinity, if both lambda 1, lambda 2 they are less than 0, then this is always going to go to the what? 0 vector, isn't it?
Yes.
Yes, sir.
This is always going to go to the 0 vector. Okay. Now I'll come back to this again, but you should understand how to plot them. How to plot them. Okay, fine. Suppose this is x, this is y. Okay. See, now let me tell you. Now my suppose this k1. K1 is something like k11, say k21, say. Fine. Okay. So now, if you look at x, if you look at that x, so that means your x equal to your c1 k11 e to the power lambda 1 t, and y equal to, and see, and for that matter, just a minute. Maybe rather than this. So then your k1 e to the power lambda 1 t, it is simply going to be this. So that means x equal to k11 e to the power lambda 1 t and y equal to k21 e to the power lambda 1. Fine. Okay. So far so good, right? Here it is fine. Okay, so that means your y by x is k21 by k11, right? Okay, so depending on, say now the next thing is very crucial. So depending upon whether k11 and k21 they have the same sign or opposite sign, so the slope of this line is going to be positive or negative. Get it?
Yes, sir.
Right? So that means if I want to draw this line, like say if the slope is positive, then it is going to be something like that, right? And if the slope is negative, it is going to be something like this. Is it okay? Fine. And yesterday I had already told you, once you eliminate the parameter t, it doesn't give you any idea about the direction. Okay. Now, if I consider my solution as a vector, then what is going to happen under these circumstances when k21 and k21 both are going to have, say, positive, similar sign. So then what is going to happen when your C1 is positive? When your C1 is positive, then these vectors C1, K1, e to the power lambda t, that is going to give you some line here in the first quadrant, isn't it? If C1 is positive. Are you getting my point? Yes? Because in that case, all x and y, they are going to lie in the first quadrant, isn't it? Right? If C1 is positive, if the slope of the line is positive, right? And then if I multiply this vector with C1, which is positive, then definitely I will have a line lying in the first quadrant. Right? If I consider this as a vector, this vector is going to lie in the first quadrant, isn't it? Fine. So that is why they are called half lines. They are called half lines. Okay. So similarly, if C2 is less than 0 in this particular case, where I am assuming that the slope is positive, so then it is going to lie in the opposite quadrant. Is it okay with everybody? Is it okay with everybody? Right?
Yes, sir.
It is clear to everybody. So if the slope is negative, then your line is going to be like this, right? And then depending upon what are the values of x and y, whether x is positive, y is negative, or x is negative, y is positive, like say the lines are going to lie in either quadrant. So those lines as vectors, they are going to lie in either quadrant. Remember that. Is it okay? Fine. They are going to lie in the either quadrant. Okay. So that is why they are called half lines. Okay. Fine. I think you have understood the concept, right? The half line. How? Yes. How corresponding to one particular eigenvector, you can draw all the vectors. Is it okay? See, if you have any doubt, just let me know. I'll still try to clear that. Okay, fine. So now let me come back to this again. So here in this particular case, you know that because your lambda1 is negative, as t tends to infinity, what is going to happen? X, y, they are going to both tend to 0. Right? So in this particular case, say suppose this is my, suppose this vector is k1, this vector is k1. So then k1 is going to look something like this. As t tends to infinity, it is going to approach 0 from both these sides. Are you getting my point? Is it okay? Fine. So similarly, say there is another one also. There is k2 also, right? There is another vector k2 also. Say in Jiten, they are drawing both the vectors k1 and k2, here in the same quadrants. Remember, it is not necessarily so. Because you will see that in Sneddon's book, in Simon's book, they are drawing it in some here, K1 here, K2 here, something like that. Okay, you don't need to worry about it. You should remember that where these vectors K1 and K2, they are going to lie, it is going to depend upon this, their respective entries, whether they are of same sign or different sign. Is it okay with everybody? Right? See, for the time being, let me follow G and Kulen. Okay, say this is K1, this is say K2. And again, you know that for K2, your the slope is going to be something like K12 and then K22. So it is going to be K22 by K12, right? This is going to be the slope. Is it okay? Fine. So now let us see the other situation. So these are the K1, K2 I have drawn, and because your lambda 2 is again negative, so if you when C1 is going to be 0, this expression is always going to give you x to be equal to C2 K2 e to the power lambda to t. So in that case, again, because lambda 2 is negative, this is going to approach 0 as t tends to infinity. So that is why your K2 is also going to have orientation like this. Is it okay with everybody? Is it okay with everybody so far?
Yes, sir.
Yes. So now, see here, what we have done, I have taken, say, these two cases in isolation I have taken. So you can, you may think that I have taken these two cases when once your C2 becomes 0 and once C1 becomes 0. Fine? Because when C1 becomes 0, then I get only x equal to this, and when C2 becomes 0, I get x to be equal to simply this, right? So in those two cases, I'm going to get these two factors, right? Okay, depending upon when whether C1 and C2 are positive or negative, I'm always going to get K1 and K2 as this. Is it clear now? You tell me.
Yes, sir.
Right? So now let us concentrate on the remaining case. Okay, if this part is clear, I'm simply going to erase this. So now this is K1 and K2 in isolation. So now let us see the overall solution. So now if you look at this, when both lambda 1 and lambda 2 are negative, if you look at the overall solution here, then you can see that as t tends to infinity, it always approaches the dominant vector K1. Is it okay with everybody? Right? And you know that a linear combination is going to give me some curve. Isn't it? They are not going to be straight lines now. Is it okay? Fine? Isn't it? When either C1 or C2 is not equal to 0, or sorry, when both of them are not equal to 0 at the same time, definitely I'm going to get some curve. Now you know that from this solution, you know that all those curves, they are moving towards what? In the direction of K1. Is that clear to everybody?
Yes, sir.
Yes. So that is why what is going to happen? Whatever other trajectories are going to be there, they are going to be moving towards K1. Okay. So how they are going to move towards K1? I'm going to show it to you. So it is going to be something like this. See, if it is coming from that side, it is going to move towards this, like this. Okay. So then, if it is coming from this side, just a minute. Here. Yeah. If coming from this side, it is going to be something like this. Okay. Okay. It is going to be something like this. Okay. So, like when they approach the point 0, which is nothing but the critical point, all these curves, all the curves, if you draw a tangent to those curves at the point x equal to 0, that is going to be simply this q1 by 1, 1. It is, the slope is going to be given by this. Is it clear now? Is it clear now?
Yes, sir.
Right? Now, this is when both the eigenvalues were negative. So now, when both the eigenvalues are positive, the opposite is going to happen. Now, what is going to happen? Here again, you know that the dominant eigenvector is going to be k1, and again here, what is going to happen? Because lambda 1 is positive, in that case, what is going to happen? It is going to move towards infinity, isn't it? It is going to move away from the critical point. Okay, so this equation is going to be same, but the thing is that here, interestingly, what is going to happen? Instead of this, the orientation going to be opposite. Okay, orientation is going to be